So this is it. This is the final video for the extra topics chapter for Physics AP. This is day 8, and it's our third day looking at capacitors. And we're going to look really quickly at what happens when you start making some changes to your circuit with a capacitor in there. So we're at this spot right here. We're going to look at what in the physics world we call transient steady states. But just before we get there, I just want to show you that these circuit animations can actually do capacitors as well. They don't like doing really big, 5 farad capacitors, but they do actually let you try it out. And I've got a circuit set up where I can charge and then discharge a capacitor. And on the left, I've got a battery here that I'm going to turn the switch on and a resistor there just for safety so I can charge that capacitor up. Notice how the current's very fast at the beginning and then slower as the voltage of that capacitor starts to build up. So I'll put a little voltmeter on the capacitor here so you can monitor it and you'll see the voltage build. Now the time constant for this one is 2 seconds if you run the math. And so we said 5 time constants mean you're pretty much done. So this whole thing should be pretty much charged in about 10 seconds. And let's just give it a quick little try here. So you'll see fast current at the beginning and then slower current later. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, is it still charging? You bet it is. It's aiming for 12 volts. But if you take a look, there's so little current flowing, and I don't see, aggressive increases in charge on that capacitor parking lot, but it is still charging. It'll take technically forever to get up to that 12 volts. Well, I'm going to stop right here and say, okay, great, we're done charging, and you can see all of that charge now built up on those plates, and now I'm going to discharge it with a light bulb. And so you'll see it go very fast at the beginning when you have lots of voltage, 11 volts, and then it will slow down. So good current at the beginning. Oh, now we're down to 6 volts. Oh, now we're only 3 volts. And the current starts slowing down and the light bulb just gets dimmer and dimmer. Again, technically it would take forever for this thing to totally discharge, right? But usually within about 5 time constants you can say, yeah, you're pretty much done. Okay, so let's take a look at these words here, transient and steady states. When we talk about steady states for these kind of circuits in physics, that means when things have been sitting for a while. It's had a long time to reach a nice stable equilibrium. More than 5 time constants, let's say. When you have that happening, you can treat capacitors like voltmeters. They're going to be a battery with some voltage on them, and they're just going to sit there with some voltage. No current's going to flow in them, and you can just treat them like a voltmeter. So in other words, when things have been sitting for a nice long time, there's no current. Current at the beginning when you're charging it up, but no current now. Now the other word you'll hear about a lot are transients, right? That's when you make a real quick change. Okay, so a transient effect is right after a change. And for the work that we would do, I would say, if you're looking at the transient story, right, as time equals 0 on the stopwatch, treat a capacitor like wires with no resistance. Right at the beginning, charge will move in the circuit, and you're thinking, oh yeah, it's just a nice continuous circuit, and actually you're just filling up the parking lot. But until the parking lot gets fairly full, you won't even notice that the current can't keep going. So it feels like a wire at the beginning. So for the last couple pages here, got this circuit. It's got a couple of just good old classic resistors, but then there's also a capacitor sitting over there that's in parallel with the 4 ohm resistor. And we're going to put a switch in here. That way we can control when things get turned on. And at the beginning, the switch is just open for a very, very long time. So it's just sitting there, nothing much is happening. And if it's been sitting there for a long time, you can treat a capacitor just like a voltmeter, just kind of hanging out, sitting here, right? Well, in this story here, if there was any charge on that capacitor, it would have been drained out into that 4 ohm resistor long ago. So in this story, V is equal to 0 for the capacitor. Now we're going to simulate this circuit here in a minute. The reason why I know the voltage is going to be 0, if there was any other Q or voltage on that capacitor, it would have been drained by that 4 ohm resistor. So yeah, it's just sitting there, 0 volts. And if you were to go and check your capacitor equation, how much Q is there? C times V. Well, there's no voltage on it, so there might be some capacitance. Maybe the things like 5 farads. I don't know. Just make that up, right? Yeah, there you are, 5 farads. Well, you can be 5 farads. If you're 0 volts pushing, then you're going to have 0 Q, 0 coulombs on that capacitor. So no charge on the cap. Okay, now let's go and turn the switch on, and we'll take a look at what happens instantly, and then we'll take a look at what happens long term. Then we're going to actually see if we can simulate it with the simulator. All right, so closing the switch. This is going to be the instant, the moment that you go and turn that switch on. So there's the switch, and you've just gone boom, and you've closed it. So this is going to be at t is equal to 0. Okay, this is going to be a transient event that happens right now. So initially, right off the start, the cap behaves like a wire. Now I know a wire will let current flow all day long, and a capacitor can't do that. But at the beginning, that parking lot is so vast, cars are going into it, charges are going into it, and you don't even notice that this eventually has to end. And so at the beginning, in that transient state, you're going to see the current come out of that battery through the switch, and it's just going to go like this. And you might be thinking, well, it can't go across the gap. Yeah, but you're not even going to notice that. You're going to notice, if you wish, Benjamin Franklin, positive charge coming out of the battery. Okay, electrons going the other way, and it's flowing. Things are good. Things are actually going to go through that 8 ohm resistor just fine, and they're going to bypass the 4 ohm resistor entirely. And the reason is that capacitor behaving like a wire, that's easier to get through than 4 ohms. So wires, okay, like this capacitor, are easier, infinitely easier really. They're easier to go through than 4 ohms. So if I was trying to figure out how much current is actually going to flow in this story, okay, so this is all initially. This is all a transient story here right now, just at t equals 0. If you go and play with Ohm's law and say, well, I've got a push with a voltage pushing and a resistance that's fighting, you've got 12 volts pushing, and you really only have 8 ohms. You're bypassing the 4. It's like you've got a wire over there. And when you run the numbers on that, you find that the current right away at the beginning is pretty aggressive, 1.5 amps. But now think about that. That's going to start to pile up on the capacitor. Positive charge on the top, negative charge on the bottom. So this can't stay this way forever. So as the I flows, as that current flows, charge piles up. So the capacitor's voltage grows. And that acts like a deterrent to stop the current from going that way. Okay, well, let's say you've now waited forever, way more than 5 time constants. So the switch has been closed for a long time. That's the kind of phrasing that you'll hear in physics stories. And you can go, oh, I get it. We're at t equals infinity. We've waited like 5 days, right? This switch has just been sitting here like this in its on or closed state for a long, long time. So this is the phrasing for steady state. No longer the transient story. And I don't know, maybe this is 5 farads of capacitance, which is huge, by the way. It's just going to behave like a voltmeter now. It'll be a charged up little battery sitting there doing pretty much nothing. So if it's a voltmeter, no current is going to flow through there. So in that branch that contains the capacitor, right here, there's no I, not in the steady state situation. So let's just go and do like Physics 11 Ohm's law work with this story to figure out what's happening in the circuit. Don't even worry about the capacitor. It's just a little monitoring voltmeter if you wish. So in this story here, my total resistance would be 12 ohms because they're in series. The total current would be 12 divided by 12. We're looking at 1 amp. Okay, checking out voltages. The voltage on the 4 ohm resistor, just going to do I times R. I've got 1 amp and I've got 4 ohms. Okay, so 4 volts on that one. And then the other 8 ohm resistor, if I do V equals IR, I've got 1 amp, 8 ohms. Okay, I've got 8 volts on that one. So that 4 ohm resistor is going to have 4 volts on it. And if I had a voltmeter sitting there monitoring that, that's really what the capacitor is going to behave like, then this voltmeter and this capacitor, they're just going to be registering 4 volts. So yeah, it'll be a charged up little rechargeable battery. In fact, if you knew that it was 5 farads, you could even figure out how much charge we've got available kind of in reserve. If it was 5 farads times our 4 volts, you could say, oh yeah, we'll have like 20 coulombs of charge all kind of piled up there. And then when you shut that circuit off, when you open the circuit up, that 20 coulombs sitting there at 4 volts is going to go, whoa, I'll keep running that 4 ohm resistor for a little bit, and it'll actually run some current in the 4 ohm resistor for a brief period of time until it finally decays. Let's see if this actually works, okay, with the circuit here. So there's the circuit. It looks kind of messy, and I've changed the resistors into light bulbs so you could actually see this run. That circuit has been open for a very, very long time. There's no current flowing at all, and you can see there's no voltage on that capacitor. There's no charge on it either. And now I'm going to go and turn it on. So here's what you'll notice. You're going to see that originally the current goes this way only. It skips the light bulb on the top, and it will light up the light bulb on the bottom. And it will do that for a brief period of time until eventually we reach the steady state where we've charged up the capacitor. So again, notice that there will be no current in this light bulb branch at the very beginning when I turn the switch on. Here goes. All right, no current in that upper branch. Oh, now it's starting. And now the current has stopped in the capacitor. And the capacitor is making its way up to 4 volts. Just, right? Technically it takes forever, but to 3 sig figs it looks like we're there. So this is the steady state. There's no current flow in the capacitor. It's just sitting there like a little voltmeter, and then it's actually like a little battery just waiting in reserve. And now when I open up this circuit, watch that upper light bulb will actually, whoop, try that again. The upper light bulb will actually keep lighting up for a little bit of time. We'll discharge that capacitor until it's eventually down to 0 volts, which technically takes forever. And that's the end of our extra topics unit for Physics AP.